for the invitation and the chance to speak here. So everything I'm going to say is joint work with Kurt Vinich, who is in Chicago, and Darren Vey, who is here. So we started working on this when I was a postdoc in Penn State with Anatol Katok, and they are both, well, Kurt graduated as a student of Katok. He is now a postdoc at Chicago, and Darren was a student of Anatol Katok. Now he's a student of Svetlana. Yeah, so what I want to discuss is Kakutani Equivalence, which is an abstract equivalence relation between measure-preserving systems, flows, or automorphisms. And, well, we are going to be focusing on this equivalence relation restricted to the class of unipotent flows. And as you'll see, Marina Ratner kind of gave the first natural examples in the sense of, say, algebraic examples for which this relation, this Kakutani equivalence, is not trivial. So she probably opened this area of research, so we pushed it a little bit further. So I'm first going to introduce the notion of what's the relation. So I'm going to start, so the setting is the general setting. It's an abstract measure theoretic relation. So we will have ergodic flows on Borel spaces. You can do as well everything as well for a single automorphism. All what I'm going to say works for a single automorphism, but since we want to discuss flows later on, unipotent flows later on, I will just present it for flows. So the first notion probably, actually you cannot see. I was hoping, because I also want to partially use the board, and this is like a like, is it visible? If not, I will.
You should let's ask her, is it no, but we want to use the board.
Let's put the screen down, and when you use the board, we put the screen back up.
Okay, but this, okay, we can do it if it's, so it's not visible. Aaron, can you? No. Okay.
It's not enjoyable enough.
Okay, so.
No, wait, he's doing it.
Maybe there will be some space left here that I can use, and on the other side. But then I need to erase, Corina, your part. Okay, so I think there's enough room. Yeah, I'm mostly going to use the slides, but some things I wanted to draw. Okay, so I think we can continue. Okay. Well, so maybe the first slide is basic, so I'll just say everything that's written, and because I just started saying that the most standard relation between flows or automorphisms is that of isomorphism. So now I'm just going to say what it means that two flows are isomorphic. So probably all of you know what it means. So there exists a measure-preserving map between the spaces on which they act, which conjugates the flows. And you know, the isomorphism problem has a long story. One of the most spectacular results here is that apart from some specific classes like Bernoulli systems or maybe discrete spectrum systems, it's not possible. It's not possible to classify, say, flows or automorphism up to isomorphism. Well, then we have a weaker equivalence relation, weaker than the isomorphism, which is orbit equivalent. So now you can say that two flows are orbit equivalent if there exists a map that maps orbits to orbits, not necessarily preserving the structure of the group R. So the orbit equivalence relation turns out to be too weak in the sense that every two ergodic flows are orbit equivalent. So we have like the notion of isomorphism, the notion of orbit equivalence, and there is an intermediate notion introduced by Kakutani. So here it goes. So now you take two flows and you'll say that they are Kakutani equivalent, the notation is here, if they have isomorphic sections, which means that they can be represented as special flows or suspension flows over the same transformation. So here I wanted to draw the first picture, maybe, I hope you can see it. So TT and ST are Kakutani equivalent if, like, I can find a function f and a transformation t, and here I find the same transformation, that's the point, that's the section, and here I have a different function g, and now I consider special flows, so, or suspension flows, that's what Corina described, right, for, say, for rotations, but you can do it for any automorphism, and you'll say that they are Kakutani equivalent if they have isomorphic sections, so this is the section, which means that they can be represented as suspensions over the same function, over the same transformation with different functions. So immediately you can see that this is weaker than the isomorphism, since if they are isomorphic, I can just take the f equal to g. And actually, one can equivalently define it. So it was also kind of defined in Corina's talk, but you can do it abstractly. So if you have a flow and a function that's in L1, you can define a time change given by the function tau of tt, and here is the formula. So you travel, the orbits are the same, but the speed with which you travel is now different. It's the function u of tx. If you have a vector field, then simply what you do is your time change flow is going to be generated by the vector field tau times the old vector field. So that's the notion of time change. And then you can say that two flows are Kakutani equivalent if there exists a function tau such that the time change of tt given by tau is going to be isomorphic to st. So essentially it's quite clear from this definition that this property is equivalent. And now we have, so what does this equivalent, so first observation is that this is indeed an equivalence relation, and then what good properties does it have? So first of all, maybe if I start with a system of zero entropy and something is Kakutani equivalent to it, well, then it's a time change. We have Abramov's formula, so everything that's Kakutani equivalent to a zero entropy system, it's going to be of zero entropy. And actually, 2 and 3 also follow by Abramov's formula. So it, of course, does not preserve entropy, so just by, say, if you change your roof, for like you take a Bernoulli, say, shift in the base and you change your roof, you might change the entropy, but if it was finite to begin with, it's going to stay finite. Okay, and then there is a notion of standard, or loosely Bernoulli, or loosely Kronecker flows. So here I should probably say that standard is a notion used by Katok. Then there is loosely Bernoulli used by Feldman. They kind of studied this this relation independently. Also, Ornstein, Rudolf Weiss, they called it loosely Bernoulli with zero entropy or loosely Kronecker. But since we worked on this when we all were in Penn State, kind of we use standard. But maybe actually loosely Kronecker is the, as you will see, is the best name probably. Okay, so now let's take a very simple flow. So you just take a linear flow on T2. So you have the two torus and a given slope, and your vector field is just constant, so you move up. And then Feldman and Katok, like I said, this is independent work. They showed that the flow with slope alpha is going to be Kakutani equivalent to the flow up. Now it's too small, but it's maybe easy to see from slide. So with the flow is Kakutani equivalent to the flow with slope beta for any two irrationals. So both of them are ergodic, and well, it's very different from isomorphism, right? So if you talk about isomorphism, of course, if alpha and beta are different, then the resulting flows are not going to be isomorphic. But when you talk about Kakutani equivalent, it follows that they are the same. And then, well, standard flows. So what are they? Well, a flow is standard, or loosely Bernoulli say, if it's Kakutani equivalent to an irrational flow on the torus. And the first part of the slide, it tells you that this is a good definition. So because any two linear flows are Kakutani equivalent, you know, you can pick any alpha, and this is not going to change your relation. So what are the properties of standard flows? No, essentially you'll see later. So it's in the flow on T2 has the property that it has zero growth in F bar metric that I will define. So everything that has zero growth in F bar metric, which I will recall in a second, is standard. So, and these are just simplest examples of standard flows. Okay, so what kind of nice properties we have? So if you have a system that's Kakutani equivalent to a linear flow, then every factor of it is also going to be, that's again Feldman Katok independently. So finite rank systems, Ornstein, Rudolf Weiss. It's also about the time I learned from Benji Weiss that this is also around the time of Katok and Feldman, just probably they didn't, like, it took some time to write it up. So in particular, it's interesting that all translation flows are standard. When you talk about automorphism, then say all IETs are going to be Kakutani equivalent to rotations. But for flows, this is what it says. Finite rank, so let me maybe use this board now. It just means that you can decompose your space and you have finitely many towers on which your system acts as a moves up the points. And since every interval exchange transformation is of finite rank, so you have like D intervals, it's going to have rank at most D. Every translation flow is of finite rank. So from this result, it follows that.
So finite rank is feasible?
Is what?
How do you see the feasibility?
For IETs? I mean, you have Rosie induction, so there are,
Finite rank.
that it's standard. It's no, it requires a proof. It's not obvious. Yeah, this is like a measure theoretic property, so it takes probably like 3 pages to prove. Yeah. Okay, so now there are some more results, again, independently. It's closed under inverse limits and compact extensions, and in particular, all Neal systems. So if you take a Neal-potent Lie group G, and the lattice inside, you take a flow generated by an element from the Lie algebra. If the group is Neal-potent, then it's also Kakutani equivalent to a rotation. And that's interesting in a sense, since, you know, Neal system might have, they have polynomial orbit growth usually, so it shows that. And here is the first result of Marina. So if you take the horocycle flow on SL2R mod gamma, gamma a finite volume lattice, then this is also standard. So this one's very different from the previous horocycle flows, like have countable Lebesgue spectrum, are mixing, so they are not finite rank, they are not compact extensions of anything. So this is a different way of proving it. Maybe I will have some time to discuss at least the sketch of Marina's proof since it's useful for us later. Okay, but then a very natural question is maybe everything is standard, and here come probably from that point of view more important examples. So first of all, Feldman constructed a non-standard system, zero entropy non-standard system. It was a cutting and stacking construction, quite involved, but still there exists one. Then Katok produced a smooth example. Essentially, there is this machinery of annals of Katok, or ABC, approximation by conjugation, and you can take Feldman's example and make it smooth. But then here is probably for the theory one of the most important examples is this one. So you take now a co-compact lattice in SL2R, and HT is the horocycle flow, and you take the Cartesian product. And well, Ratner showed that this one's not standard. So like a very natural example for which we have something that's non-trivial. So it's interesting. Maybe I would need. Maybe I can use some, because yeah, there's no eraser. So okay. So like Ratner's result, they tell you two things. So for the horocycle flow, you can find a function g, say, such that the horocycle flow ht is isomorphic to a flow suspension over the rotation. So again, okay, which is quite remarkable when you think about it, since you know the rotation is a very low complexity. It's like a very elliptic system. So the function g kind of carries all of the non-trivial dynamics of the horocycle flow. It's you know, you can make it continuous by an abstract theory, by abstract results, but the function will be quite wiggling most likely, since you know you have to make it mixing, so it has to be quite an irregular function. But then probably a more important result from this point of view is that if you now take ht cross ht, then you cannot do this. So there does not exist an L1 function for which, or a continuous function for which you would have this isomorphism. And well, already maybe one can see it a bit here. It doesn't sound trivial, right? Showing that the function in L1 does not exist is seems to be a tough work. So I should say probably that Ratner was motivated by an example of Ornstein-Rudolph Weiss of a rank 1 system whose product is not rank 1, as far as I understand. So this falls into this category. And then, well, what else? So we have standard systems. So, but how about general Kakutani equivalence? Well, so we have uncountably many pairwise non-Kakutani equivalent systems. They are the construction is a modification of Feldman's construction. So again, it's a cutting and stacking method, quite involved. But then Marina Ratner in a different paper showed the following. So gamma is a co-compact lattice, and now you take the kth copies of the horocycle flow and L copies of horocycle flow, and then she showed they are not Kakutani equivalent if k is not equal to L. In fact, so if k equals 2 and L equals 1, this is plus the fact that horocycle flows are standard, it follows the result on the horocycle square is a special case of this result here.
Can you give any intuition how does one show that two flows are not
Yeah, this is what the talk is like. That's where I'm heading to. So I will definitely give you some. Actually, probably on the next slide it's going to appear. So a good question that, as we see, is natural is how to show that two systems are not Kakutani equivalent. Well, usually you need, so one way of doing it, and that's actually the way that Ratner uses, is to introduce an invariant of the relation and then compute it and show it's different. Well, so that's like a very abstract method. So, well, So Kakutani invariant. So for automorphism, this was done by Feldman. Since we are talking about flows, Marina Ratner modified Feldman's construction to flows. So, well, how do you prove that two things are not Kakutani equivalent? Well, you introduce an invariant. So the EU of TT is an invariant. It's a number for any flow, say ergodic flow, and the function U that you fix at the very beginning. That's called a scale maybe. And well, you want that if two flows are Kakutani equivalent, then the invariants are going to be the same. And then, moreover, what Marina did in her definition in her paper, actually this is a theorem. So if you have zero growth of this invariant for any scale function U, then you are standard. And this kind of answers the question of whether there is something special about, say, linear flows on T2. Why do we talk about them? Well, any flow that gives you zero of this invariant that I'm going to define just right now is good for the notion of standardness. And the key point for the invariant is the new way of measuring when 2 points are close, and this is done in Feldman's paper. It's the F-bar metric. So first I'm just gonna probably read it, and then on the next slide I have a picture. So you start with a flow and a finite partition, and you take an epsilon, and you say that 2 points are epsilon matchable or for time t if you can find a measure preserving map from the interval 0t to 0t up to an epsilon error such that ttx and tht of y are in one atom for the large measure set. Okay, so the usual probably notion that we are familiar with is the d-bar metric, in which h is just identity, right? So, and this this is what also motivated Feldman. So he wanted, as far it's stated in his paper, so he wanted to relax Ornstein entropy theory by switching the metric. So in the usual metric, what you do is you take h equal to identity, and that's the definition of 2 points being, say, close. And the picture here is that you are allowed to slide up. The difference here is that you are allowed to slide along orbits. So d-bar metric, you look vertically what happens. Here you can slide along the orbits in a measure preserving way. So the green part is the matching, say, of x and y for time n. And maybe just to show you some differences. So for instance, if you take the most apparent example is if you take, say, x and t of x, so the time one map of x. So in the d-bar metric, when you just look vertically, they are not good. There is no reason in general for these two to be close, right? So if you shift and then they are one apart. So if your partition, say, is regular, they are not going to be in one atom. But here what you do is, if you take the orbit from 0 to t and the orbit from 0 to t, you just skip the first coordinate, and your matching function h is just going to be like this, right? So it shifts by 1. So they are f-bar close always. And there is nothing special about the 1. So if I take ts for some s, say, less than epsilon t, I can do the same thing, right? So I just shift by s, and this defines my h. Okay? So a hint for now, I'm going to discuss it in more detail in a moment, but why horocycle flows? Well, remember, so from the previous slide, something is standard, so we have a nice way of checking if something is standard. If you look at the third dot, you just need to show that, well, whatever the invariant is, it includes the f, to define it, you need the f-bar metric is 0. So actually what you need to show is that any 2 points are in one ball, F-bar ball. So you can match any 2 points. And just let me highlight it. I'm going to go in more details in a sec. Like horocycle flow have this property that most of the divergence happens in the flow direction, which kind of allows us to see this picture not only for points in the same orbit, but for any 2 points that are close, for instance. Yeah, so, and now once you have this F-bar metric, then Feldman's construction that was here adapted to flows by Ratner is the same as that of entropy. So you count the number of F-bar balls of radius epsilon needed to cover most of space. Then you take, well, you have fixed the scale u of t. You take lim inf. Then you take lim sup as epsilon goes to 0, and then supremum over all the partitions. So this part is standard, like steps 2, 3, and 4 are exactly the same as in the definition of, in one of the definitions of the usual entropy. The only difference is, what does it mean that 2 points are close? So here you have the F-bar ball. For the usual entropy, you have the D-bar ball. Moreover, for the usual entropy, u would be e to like an exponential function. Here, almost always you take something slower, like log t. Okay, so if only you can digest the definition of F-bar metric, then the rest of the definition of the invariant is just like entropy. And actually, that's what Feldman says in his paper. Okay, so then we have some nice properties. So like with the entropy. So this is going to go in parallel with entropy. Just keep in mind that we have different metric on the space. So if you have a generator, you have a useful way, an easy way. It's not easy, but a useful way of computing the invariant. So it's enough to compute it on generator. Moreover, if you have a sequence of partitions that converge to a point partition, then you have you need to be able to compute the following limit. So these two are like the same as for the entropy, right? And then, well, TT is standard. So Ratner proved that TT is standard if the EU of TT is 0 for any U, which essentially means that the number of F-bar ball does not depend on T. Okay? So it means that this number here, right, if you have it for any U, then ST epsilon P in fact does not depend on T. So it stays bounded. It might depend on epsilon, but it stays bounded. Okay, so that's a very useful way of showing that something is standard. Now I want to point out that if you now do D-bar instead of F-bar, then you would get rotations. So the only, like if you think of systems that in the D-bar metric don't grow at all, then you have rotations. And maybe that's why loosely Kronecker seems like the right notion, for instance, because, well, it depends on your taste, but like Kronecker system give you 0 in D-bar, so here we have F-bar. So what Ratner showed is, now we can say, if you take the horocycle flow, Ratner showed it's standard, so you pick any 2 points and you should be able to match them with respect to this F-bar metric. That's what she has done. And the key property is the shearing, or the Ratner property, that allows us to say that if I take 2 nearby points, they are going to split in the direction of the flow. So I'll have a nice matching, because the function h, remember, F-bar metric is actually designed to deal with things that split along the flow, right? You can then shift it. Maybe one more comment is that if you take something, another unipotent flow, where you have a bigger centralizer, then it's a tricky question to say. Actually, this is what we'll do. But So now if you think about HT cross HT, so her other result, that it's not standard, so you need to show that there are essentially, it boils down to showing that there are 2 points which you cannot match for HT cross HT. Okay? And here, I'm gonna maybe just now say, but here what you're using is that, well, on the product space, unless the points are on the diagonal, the divergence in the first coordinate is going to happen with different speed than in the other coordinate, right? So matching it on the first coordinate is not compatible with matching it on the other coordinate unless the points are on the diagonal, in which case they split the same with the same speed at the same time or close to the diagonal. Yeah. So what Marina showed, so if you take the scaling function, so the scale log of x, then the invariant is in this interval, 3k minus 3, 3k minus 2. Okay, so this allows her to deduce that, well, if you take two different ones, you have this intervals, they are going to be disjoint, so the invariant gives you a different value, so these flows are not Kakutani equivalent. So this, I hope, answers the question how to show. Also, let me point out, since this is going to be important further on, that she crucially, so Marina crucially uses the co-compactness of the lattice. So in the finite volume case, for instance, SLNR mod SLNZ, this completely breaks down the proof in the sense that she uses the fact that the lattice is hyperbolic. So.
Is it none of the proof?
So that's what actually I want to discuss in particular. And then, well, in the 90s, I think, or yeah, 1994, she asked a question, okay, so the HT to power k is a very specific example of a unipotent flow. So she asked this question, and this is what we studied, what we are interested in. And so let me just say what the setting is for the, okay, what the setting is for the second part. So you take G, a semi-simple Lie group with the algebra. You take an unipotent element. So unipotent elements, they are elements whose adjoint operator given by this formula is nilpotent. So you can think about really SLNR if that's enough. It's already showing all the complications and all the, say, results. So SLNR mod gamma is enough, or maybe products of SLNRs, so matrix groups. Well, then gamma is a lattice, and then we take this one parameter family. And to state our main result, I need to recall some basic facts about, say, unipotent or nilpotent elements. So, so this is chain basis. So if you have a nilpotent matrix, you can, it has Jordan blocks, so let me maybe erase this part. And the chain basis is just a consequence of existence of Jordan blocks. So adjoint U is a nilpotent matrix, so you can represent it like this. Say, it's not maybe the best picture since it should be more a square. Like this, so you can represent it in some Jordan blocks, right? And the chain structure is nothing else but it's just the way that the adjoint acts on each Jordan block. So for instance, if I fix I equal to 1, I take the first Jordan block and I have the standard basis of the size of the dimension of this block, and then it's just the adjoint is just going to move from one vector to the other until it hits something that goes to 0, and the last element by definition, right? So the, say, xi1 has the property that it commutes with u. So xi1 is in the centralizer of u. Okay? So for any nilpotent, unipotent element, you have this chain basis. So for instance, for the horocycle flow, you just have one chain of length 3, so it's just going to be the opposite horocycle goes to geodesic, and then it goes to the horocycle the centralizer is essentially the flow. For the product, you'll have two chains. One is going to be the SL2R triple, and the other one is splitting in the direction of the centralizer. Maybe an important comment here is that this decomposition, it tells you a lot of how points behave. So just if I fix one chain, then, and I take, say, 2 points in my space that differ in this direction, then the speed with which they split is going to be mi, so polynomial of degree mi, and the direction in which they will split is going to be the centralizer, the last element. Okay, so if you take the horocycle flow, for instance, I like to call it v goes to x goes to u, so this is 0, 0, 1, 0, 1, and 0, 1, 0, 0. So if you just take this chain, it tells you that if you take 2 points in the opposite horocycle, so in the v direction, the growth is quadratic, and they split in the u direction, which is the flow. Now, if you take 2 points in the x direction, the growth is going to be linear, so you need to wait about the inverse of the distance for them to split, and they still split in the flow direction. Okay, so notice for the horocycle flow, if only I take two close points, everything, the space is three-dimensional, everything splits in the flow direction. And that's very special about the horocycle flow. Okay, if I have two chains, say another chain, say if I think about products of horocycle flow, then of course I have still polynomial speed of splitting, but it's not the flow anymore. Okay, the last element is some element from the centralizer, but since it's a basis, it's orthogonal to the flow. Okay, and then you introduce the number GRU, which is just this number. So using I think it's maybe Gauss summation. So this guy comes with weight mi, mi minus 1, mi minus 2, mi minus 3, and so on, and you sum all of them. So like this chain would give you growth 1/2 mi times mi minus 1. You sum all the numbers from 1 to mi, and then you sum over all the chains. Okay, so this is like the total growth that your unipotent exhibits. For the horocycle flow, notice I have one chain, so the summation here is just over one element, and I have two, well, it should be 2 plus 1, so I have 3, right? Maybe now I'm thinking there is a, maybe the index is shifted. No, it's okay. So yeah, it's going to be 1 plus 2. So 2 for the v and 1 for the x, so it's 3. Okay. If I have now, for instance, two chains of length 3, then I will have 3 plus 3, which is 6. And if I have, and this is actually the decomposition, the chain decomposition for the kth product. So if you take the kth product of the horocycle flow, you'll have k chains of length 3, so the GRU, the growth is 3k. Okay, and what we proved is the following statement. So you take the same scale as Ratner did, and you take a unipotent flow on G mod gamma. No assumptions that the lattice is compact so far. And then you can show this bounce. You can show this bounce. If gamma additionally is co-compact, then you have exact asymptotics. So it's GRU minus 3. And, well, so if the growth is 3, then the flow is standard. Okay? And here is a comment. So in this setting, there always exists an SL2R triple. So you always have this chain. If for every unipotent, one of the chain is the SL2R triple, so it behaves like for the horocycle flow. Hence, the growth is at least 3, right? GRU is at least 3. So, some maybe comments, some things to notice.
With the definition of GRU.
Sorry?
The definition of GRU.
Yeah, it's here. So you're summing the weights, like mi plus mi minus 1 plus mi minus 2. So this gives you 1/2 mi minus 1, and then you're summing over all the chains. So maybe some simple observations. So notice that by what we have, it's very hard to have GRU equal to 3 actually. So there has to be something special, and we'll say it in a second, about the U to have growth 3, right? The only way you can have growth 3, and actually that's how we prove this, is if, maybe I have it as one of the consequences. Yeah, so this is the statement. Growth GR equal to 3, it means that you just have one chain which you need to have coming from the SL2R triple, yes, so VXU, and then all the other chains, this already gives you 3. So if the growth is 3, so I remind you the third part here, then it means that all other chains are just of length 1. So x1, x2, x3, they are all trivial. So, but the last element of the chain is an element from the centralizer of the flow. So it means that apart from this SL2R triple, everything is in the centralizer. Okay, so the flow has to be of the form, that's what we show, identity, which corresponds to the centralizer part, say, right? If I have identity, it commutes with everything, so this is the identity, and here we have 1T01. Okay, so they are quite special. Moreover, if the dimension is larger than 3 and we have like SLNR, then no unipotent flow on Gmod gamma is standard. This just follows from the fact that we show that, I mean, it's an exercise to show that there always has to exist a one non-trivial chain. So some examples. So for instance, if gamma is, our computation, it shows 3k minus 4, 3k minus 3 if for general gamma, like for SLNZ, but if gamma is co-compact, then we have 3k minus 3, the exact one. Ratner computed it to be 3k minus 2, 3k minus 3, so the upper bound in Ratner is the correct one. And I hope to have time, yeah, I still have to have time to at least try to convince you why this is the correct, maybe number. This is the ideologically the correct value. Well, then I just gave one example. For this one, there is one chain of length 3 and another chain, the algebra is 8-dimensional, so there is another chain of length 5. Which, if you just plug it into the formula, it gives you that the GRU is 16, so if you subtract 3, it's 13 or 12. So now it's very easy to say, you know, given it's very easy to construct examples that are not Kakutani equivalent. This growth number, notice that it does not, where do we have it? This does not depend on the lattice. So if you have a unipotent element, not yet a lattice, you can compute this number, and you take another unipotent element on a possibly different group, then you already know that, and it comes, these two numbers are different, then you already know that they are not Kakutani equivalent, no matter what the lattice is, say co-compact. In the non-co-compact case, there is this subtlety that we still believe, of course, that it's the same, but the fact that you the systole is not that you can escape to the cusp kind of produces a difficulty that we can't bypass. So you can, yeah.
If it's standard, then that implies the growth number is either 3 or 4.
Actually, we show that in this case it has to be 3. Yeah, in this case. So.
Which is, I mean, in general.
No. So you take a standard flow, then GRU equals 3. That's the question, or? Yeah. If only it exceeds 3, so it's like 4, then yeah. Okay, so these are the examples. Let's see. Okay, so now what I want to do for the last 10 minutes, I just want to hopefully convince you that the upper bound is what we would expect. Okay, this one's not difficult. The lower bound is way more difficult since, well, the lower bound allows you to show in particular that something is not standard, and as we saw, it's quite hard to show that it is not standard. But let me try to convince you that this is the maximal number you can hope for, and this shouldn't be. The upper bound shouldn't be difficult. So maybe let me go back here for a sec. So as I said, you can, instead of looking at say F-bar metric, you can work with D-bar metric in the sense that you just talk about bow and ball. So how close do I need to take my points for them to stay together for time t, for instance? And this is the number. So the if I take a point x, and I'm looking for all the points that are going to stay with x together for time t, I need to go like t minus mi minus 1 in all the directions. I mean, it's a double summation. So, but we very well understand what it means for 2 points to be close up to time t. They essentially need to be mi close, t to the minus mi close in this direction, mi minus 1 in this one, and so on and so forth. So for instance, for the horocycle, I need to be like t minus 2 close in this one, and t minus 1 close in this one. Then I know that for time t, I won't split. So this number, GRU, it gives you the asymptotic growth, right? So t to the minus GRU, or t to the GRU is, say, the asymptotic growth in the D-bar metric, so in the case of bow and balls, right? So definitely, trivially, and this is what I think I have next, a trivial bound, so sorry, I have n instead of t, but like a really trivial bound is n to the GRU. And this is the bound which is very rough, in which I don't use F-bar metric at all. If I have 2 points, I just simply connect them vertically. So it's the simplest H is just identity in this case. Okay? But this is not everything. And now comes the less trivial part. So first of all, we said that F-bar metric you allow to slide along the orbit. So trivially, you can match point x and ttx. Right? They are F-bar close, even though they are not D-bar close usually, right? So this brings you down to GRU minus 1, right? There is one direction in the Lie algebra, which is the flow direction, the u direction, in which you don't see. So trivially, by the properties of F-bar metric, you are down to GRU minus 1. Then we have the geodesic direction. So if I take 2 points in the geodesic direction, then, well, we have the renormalization equation, which I've presented here. So if S is small, say S is of size delta, then it's enough to take my h of t to be just e to power 2s of t, right? Just the whatever the time parameter here gives me. Right, so this is the shearing that we saw before. So now the matching is just going to be S is small, so this is close to 1, the derivative is close to 1, so it's measure preserving, it's just going to be more and more like this in a linear way. Right? So this brings us to GRU minus 2. I can match 2 points in one orbit, first of all, 2 points in one geodesic direction. Now what happens to the V? So the opposite horocycle direction. This is a little bit more tricky, but not that much. So now, if you take 2 points in the opposite horocycle direction, the main splitting or the main divergence happens along the flow, but there is also, and this is quadratic, but there is also a linear divergence which is in the geodesic direction. Okay, that is, say, bad in the sense that once points split in the geodesic direction, you can't hope for f bar. F bar, allows you to slide along the orbit, not along the geodesic direction. But if I know that I have 2 points in the opposite horocycle direction that are 1/n distant, or I mean maybe up to some epsilon, I'm neglecting the epsilons, then I'm going to see the divergence only in the flow direction and not yet see the divergence in the geodesic. So in other words, I can always match the following. If I have an x, so I can draw a cube of size delta in the u direction, delta in the x direction, and 1/n in the v direction. Okay? If I take a point x here, and I have this cube, sorry, then everything in this cube is going to be f bar close. Okay? These two are just, this is trivial, this is by the renormalization, and this is by the fact that the geodesic has not time to enter. Maybe there is a, there is an epsilon inverse here, just, but we are talking about the order, so it's of order 1/n. Well, the size of this cube is, say, delta squared. Let me put a delta here. Delta cube times n, times 1/n, right? Okay, so if, this is now the, so what I need to do to say, now I want to show that, say, this, by the way, so this brings me down, sorry, to GRU minus 3. Okay, so this is the correct growth. Okay, GRU minus 3, that's why it appears, that's why it appears, and also by now I think we can show why horocycle flows or heuristically are standard. So if I take any 2 points, you need to be able to match them in an f bar ball, x and y. What I'm going to do, I'm going to wait with the orbit of y till it enters this box. And when it enters, I can match it. So the picture is like this. So I have the orbit of x, the orbit of y. Here I wait for some time of size roughly n again. The cube has size 1/n, so it takes about n to enter it. And actually, I'm going to enter every such cube. This is, here we are using the property of the horocycle flow. And then I'm in a situation where I have a good f-bar matching here, right? And if this is negligible, I can match all points. Okay? So the lower bound is, it's quite easy to get. The upper bound, sorry. The tricky part is the lower bound. Well, and here I'm just probably gonna very roughly say what. So the idea is, since we show that the lower bound is also GRU minus 3, so now you need to show that that's it. Like all other directions you have, you cannot match the points actually. And this is the hard part in Ratner's argument. That's where she uses the fact that the lattice is hyperbolic. But a very rough idea is, which is really one has to go, there's lots of details, but one very rough idea is that all other points, except these 3 special directions coming from DSL2R triple, they split in the direction of the centralizer. Okay? So all directions except UV and X split to a direction that's orthogonal to the flow. And, well, F-bar matching, it works very nice when I split along the flow, but when I split along the centralizer, kind of orthogonally, you need to show that you can't, that such a matching is not possible. So maybe one last slide. So there are some things that we work on, or maybe some questions. So first of all, yeah, as we said, we don't know what happens if you change the lattice. The invariant is obviously the same. As we said, GRU does not depend on the lattice, it only depends on the Lie algebra or on the group G and the unipotent. So now what happens if you change the lattice? The only non-trivial result here is that if U is a horocycle flow, then Ratner showed that everything is standard, so this is the case, but for other, there are no non-trivial. Yeah, here the other thing that we want to study is you might have two very different flows on very different groups that give you the same invariant, right? It's just the Jordan block structure, so you can easily come up with different Jordan block decompositions, different dimensions, and still get the same invariant in the end. So the hope is, say, using, maybe the fact that unipotent flows are rigid, that this is the case. So if the invariant coincides, then you can indeed. And maybe last question that kind of came up when I discussed with Federico. So in dimension 3, does K, so now we talk about smooth. So the third question is not about unipotence anymore. So like you have a K system, Kolmogorov property, you have a smooth system in dimension 3, does it imply loose Bernoullicity? So here it's positive entropy, so loose Bernoullicity is the right name, and this just means Kakutani equivalence to Bernoulli shift. It's a yeah, but absolutely. But the question is, so you have a smooth system in dimension 3. His is TT inverse, so it's just continuous, not smooth. Right. So this is a question about smooth realization. So for instance, imagine that I can show that in dimension 3 K implies loose Bernoullicity, then I cannot realize Kalikov in dimension 3. Yeah, that's actually the idea. Yeah, so that's it. Thanks.
Time for questions.
In the non-compact case, you know that the invariant is from interval.
Yes.
That can be not boundary.
We strongly believe that it's the right endpoint. So it's the same as in the compact case. It's just that when points escape to the cusp, the systole becomes small and we can't make the computation work, but it should be okay. That's a good question. So standard maps, they have, let me think. Actually, it's very hard to come up with something that's not standard. So I think the fact that unipotent flows give, because before it was like these abstract constructions that are beautiful but kind of, built to not be, and then, two Ratner's results. So these are essentially the first examples where you can really understand what's going on. So I don't know if taking a different, for instance, if here you take a different scale, then you are infinity or 0, so it's just not useful. Yeah, I don't know. That's a good question, maybe.
Okay, let's thank Adam again. So there is a short break now, and we start again at 3:30.